So 25 minutes, I'll try and give you a kind of tapas introduction to heavy fermion materials and why I think that they're still very relevant for our research into quantum materials today. This is a talk that I hope will encourage discussion not only amongst the cognoscenti but also amongst the students. I may not get past my introduction, that's fine, because this is an introduction anyway. And please don't hesitate to even interrupt the flow of conversation if you've got a burning question. Okay. So I'm going to basically talk about three small topics in heavy fermions, each one of which is wide open at the moment, and each one of which has a connection with interests in d-electron systems, topological systems. Since I've been working in this area for a long time, I have many collaborators. I'm not going to read them out to you, but this is a quick list, and of course the work has been funded, particularly by the US Department of Energy and NSF, although they never want to admit that they overlap with each other. Okay, these are some overview articles that I've been involved in, and they'll be on the PDF. Okay, so this is my outline. I'll give you an introduction to heavy fermions, why they're a fruit fly for strong correlation. I'll introduce an ancient question and give you a brief cartoon introduction. And then I'll illustrate the area by trying to hop, skip and jump from quantum criticality to topological Kondo insulators and to hidden order, although I suspect I won't make it to the final topic. But it'll all be there in the PDF, and so let's see where we get to. So why do fundamental research? There's a question that is particularly pertinent in Britain, where there's a strong pressure to come up with applications because all the interesting research has been done, and now is the time for our spin-offs. And I want to remind you about the role the fruit fly played in the 20th century, long before the discovery of DNA. People found that they could make amazing progress in biology by studying the fruit fly. Because it breeds rapidly, it's very easy to make several generations, and of course it's completely irrelevant to food production unless you plan to eat flies. Nevertheless, it enabled the world to move ahead dramatically long before the advent of molecular biology. In a similar sense, when we go to the 21st century, of course we have many pressing problems, and we seek paradigm shifts that will help us solve these major problems. And one way to do it is to go head on, but the other way to do it is to buy the lottery ticket of research and look for materials that can help us gain insight, perhaps will provide a roadmap for the key issues that are ahead of us. And one such class of materials are the heavy electron materials. This is a little picture of a plutonium cobalt gallium 5. It's a 20 Kelvin superconductor, and it's a material which is a miniature version of the cuprate superconductors. Okay. The other aspect I wanted to draw to your attention is that really, as we span between the nanometer, where we would love to engineer, and the micrometer, where we can already engineer, we have major issues of understanding. At the nanometer scale, we understand things very well, but as we go from the nanometer to the micron, collective behavior develops. And the character of that collective behavior spans all the way from high-temperature superconductors to life itself. Okay? So this is the frontier that we're working on. And of course, everyone knows about the applications that we are seeking. So what about a map for quantum matter? And if you look at the old maps, you see that they were very primitive. You look at that and might scoff at it, but our understanding of quantum matter is equally primitive today. And so I want to remind you about where the map lies, where the fabric lies. That's, of course, the periodic table. And we're particularly interested in using interactions to drive new behavior. And so one way to enhance the interactions is to look for orbitals that are very tightly bound inside the atom, but nevertheless partially filled. These are the d, f, and f orbitals. And this is the order of increasing localization. Notice that the 4f are the most localized orbitals. And years ago, Komenko and Smith used this as a way of reorganizing the unfilled rows of the periodic table into their diagram here, which shows localization increasing upwards and towards the right. This is the actinide contraction. And as they pointed out, as you go from bottom left to top right, you go from highly itinerant elements to highly localized magnetic moments. And the crossover region is very interesting to us. This is where many interesting phenomena occur. And so cerium heavy fermion systems, uranium, neptunium, plutonium heavy fermion systems, manganese and iron and copper are all at this crossover. And the basic message is that many things are possible at the brink of localization, where itinerancy and localization are competing with one another, and degrees of freedom are being released that can be used to drive new forms of entanglement. Okay. So let me remind you of the standard model for kinetic matter physics, and tell you about what is a very ancient question. Okay. And of course we've all learned, or we're learning, about Landau's wonderful phenomenological theory of the Fermi liquid, and the idea, the paradoxical idea, that interactions can be turned on adiabatically, preserving the excitation spectrum in a gapless system. And he used this to great effect to understand and introduce the concept of the quasiparticle, which is the mainstay of our understanding of conventional metals and semiconductors. They carry the spin and the charge of the non-interacting electron or the non-interacting fermion, and the classic application that he used it for was liquid helium-3. The other thing he did was to parameterize the problem in terms of various parameters, such as the dipole interaction, which in a translationally invariant system, a Galilean invariant system, sets the mass for normalization. But Landau's idea, and here is its application to helium-3, where you could explain the mass enhancement of 2.8 in terms of this one parameter. But Landau, here's a picture of Landau. Who knows which guy is Landau? Students. Any student know which one is Landau? How about him? Is that Landau? No. Who's this young guy? It's Freeman Dyson. Okay, and this is Lev Landau, and they're talking. In fact, they probably both had a lot of respect and a certain amount of contempt for each other this meeting. And there are various other people here, the late Anatoly Larkin, Pomeranchuk, and Abrakozov. And one of the discussions at the time was the Fermi liquid. Landau described his theory for the Fermi liquid to Dyson. And Pomeranchuk was very worried about when Fermi liquids might go unstable. One of the things you can do is imagine what would happen if a guy came back from the future and asked them a question. So here's my guy coming back from the future. It's the late Ken Wilson. And what happens when the interaction becomes too large and the Fermi liquid becomes unstable? And there are many answers to this ancient question. One is that you get an instability, an electron's order. Another is that electrons localize. This is an idea that was pursued initially by Piles and Mott, and then later Anderson pointed out they localize and they form local moments. Okay? And then later, in the 70s and 80s, Hertz and Doniach realized that the point of transition was interesting. And nowadays we know that this point of transition is a quantum phase transition, or possibly a quantum critical point, which nucleates new forms of matter and also drives the development of strange types of metals that don't fit in to the Landau Fermi liquid picture. And last but not least, Wilson himself would have said that all of this stuff is described by the general concept of fixed points, new fixed points, attractive fixed points, which are stable phases, repulsive fixed points, which are critical points. And in the modern context, we would call these fixed points new forms of electron entanglement. That's what we're interested in. So, in a general sense, this is really a message that affects across the field in the 3D systems and the 4F systems. Many of them exhibit interesting behavior, in particular superconductivity, around a quantum critical point that separates magnetism from itinerant electron behavior. What we really need is, in a general sense, a unified conceptual description of magnetism, quantum criticality, and superconductivity. This is still lacking. So let me tell you how heavy fermions may play a role in this. This is a cartoon introduction. One Hamiltonian, mainly pictures. Here is the spin, cartoon of the electron spin, and of course in reality an electron spin is a more complicated problem. In heavy electron systems there's strong spin-orbit coupling. This couples the spin and the angular momentum together into a multiplet, which is then split typically into doublets or singlets by the crystal field. And it's those doublets, those multiplets, that play a role in the physics. And the way you know they're there is they produce a Curie-Weiss susceptibility, the simplest way of telling they're there. But these local moments don't live in a vacuum, they live in a metallic environment. And it's that interaction of the spin with the metallic environment that's really so fascinating, because it leads to a variety of entanglement phenomena. One of the things you can do, which Kondo himself did in 1962, is to ask, well, what is the basic weak interaction? And the answer is it's anti-ferromagnetic. It's an example of super exchange coming from high-frequency valence fluctuations driving low-frequency anti-ferromagnetic interactions, which, although they're very weak, they have the property that they get stronger at low temperatures. This is the origin of the resistivity minimum, first discovered in the 1930s, which grows as you go to low temperatures. And later on, it was understood that this growth at low temperatures is because this coupling constant scales from weak coupling to a crossover, and then ultimately to strong coupling. In the simplest cases, it just screens the local moment, forms a singlet, the simplest form of entanglement you can possibly imagine. That's a Kondo singlet, and it scatters electrons elastically. Moreover, the entropy of entanglement can be seen from the specific heat capacity. If you integrate specific heat capacity up to the Kondo temperature, which is an emergent scale, you get about half log 2 per spin. And that's it. My own advisor was said to have burnt 3 graduate students on this problem. It took 10 years to understand this one issue, and it was 30 years from the first discovery of the resistance minimum to the understanding of this problem. It required the development of new conceptual frameworks, particularly the renormalization group. The basic idea of scaling to strong coupling is intimately connected with the notion of quark confinement. Okay? And so you can see here that anomalies in data seen today may well require 30 or 40 years for their full understanding. Okay? And another 50 years for them to change the paradigm of the research. This is what funding agencies just don't understand. So, well, this is one of the things when you embed these local moments in a metallic environment, they start to interact in a new way. And Sebastian Doniach in 1977 pointed out there are 2 interactions that come into play in a lattice: the Kondo temperature, which is this singlet formation scale, and the RKKY scale. And when the RKKY scale is smaller than the Kondo temperature, you can form singlets at every site. And when that does this, the local moments kind of dissolve into the conduction fluid and they become mobile. They form a large Fermi surface of composite fermions. And Doniach realized that in between these 2 extreme limits, you might have a quantum critical point. And that's what he mentioned in his paper of 1977, that second order condition at 0 temperature. So that's the end of my cartoon introduction, but I want to point out that empirically, this entanglement takes many forms. And one of the things you can see is that it leads to the formation of heavy electron metals. And you see that because the resistivity doesn't continue to rise indefinitely, coherence develops, and you form metallic behavior. Serum aluminium-3 is one of the classic examples. But there are other kinds of entanglement, for example, new kinds of superconductor. Uranium beryllium-13, although discovered in 1983, remains an unsolved problem of superconductivity, mainly because this large area of entanglement here that forms the superconductor is spin entanglement. It raises the question, how do spins entangle to form superconductors? Okay. And so, in general, these are interesting systems because they have very close by a quantum critical point. And that quantum critical point is an unstable fixed point, and as Wilson would point out, it can flow to a variety of stable fixed points: antiferromagnets, multipolar order, superconductivity, new forms of order, and of course the Landau Fermi liquid, and we could add to that also insulators. Okay. So these are some pictures to illustrate the point. Here's uranium beryllium-13. There are new kinds of insulator. I'll talk a bit about samarium hexaboride, which exhibits topological conductivity on its surface. There are new kinds of electron order. One of my favorites is uranium ruthenium-2 silicon-2, which has these unusual Ising mobile electrons. And well, is one that I won't talk about today. This is a neptunium superconductor that goes directly from a Curie paramagnet directly into a superconductor. And these local moments entangle with the electrons to form the superconductivity, suggesting there may be some kind of composite pairing here. Okay. And last but not least, there are new kinds of phase transition. And I'll begin with that because really we still believe these quantum critical points are the nucleating points for new types of quantum entanglement. Chairman, how much time have I used up?
10 minutes left.
10 minutes left. Okay, good. Okay. So, let me tell you a tiny bit about quantum criticality and why it's still an unsolved problem and many people are trying to come up with new ideas. A quantum phase transition is a phase transition that occurs at 0 temperature driven by 0-point energy. And here is an example, a terbium rhodium-2 silicon-2, which exhibits field tune criticality. If you cool it down at 90 millikelvin, it becomes antiferromagnetic, and the order parameter is a staggered magnetization. But as you increase the magnetic field, quantum fluctuations destroy the order and lead to a quantum critical point. Okay? So whilst we understand this transition, we don't understand this transition here, particularly in metals. One of the things that happens when you hit this quantum critical point, and this is the orange region, is it develops a linear resistivity. It goes from quadratic resistivity, which is blue, to orange, which is linear resistivity. And this is a sign of the breakdown of the Fermi liquid. And this linear resistivity extends up to quite high temperatures for this material, certainly up to 1, but maybe up to 10 Kelvin. And this kind of linear resistivity, or quasi-linear resistivity, is seen in many quantum critical systems. It's seen, for example, in quantum critical ionic type systems. And we don't really have a good explanation for it. This upper temperature scale in the cuprates can be as high as 1,000 Kelvin. Okay? But one idea is it may be driven by quantum criticality. Okay? Here is a cartoon of quantum criticality. As you tune some parameters, such as pressure, you go from antiferromagnetism to a Fermi liquid. Here is a real system, serum copper 6 gold, where the gold tunes negative pressure, drives you actually from the metal into the antiferromagnet. You can see the antiferromagnetic transition. And notice that C over T has a logarithmic behavior at the transition. This logarithmic behavior is a sign of the breakdown of Fermi liquid behavior. And many systems exhibit this behavior with a characteristic temperature scale T0 and a Q here, which is typically of order half log 2. And this tells us that the mass has gone to infinity and a breakdown of Fermi liquid. And although a lot of effort has been expanded on this problem, and some of the systems can be understood in terms of a kind of spin density wave transition, there are many bad actors, such as this system, which don't fit into that behavior. And we're looking for a new description of this quantum critical point. This is the standard model, the quantum spin density wave picture, and often known as the Millis-Hertz approach. And the basic idea is that quantum criticality is driven by soft magnetic fluctuations, which induce long-range interactions that break the Fermi liquid down. The problem with this model is that actually time counts as 2 dimensions in the scaling theory, and this means that when you're in 3 spatial dimensions, these soft modes don't interact strongly at long distances. You get what is a Gaussian fixed point. Whereas to understand the unusual physics of these systems, you need to have something that would involve interacting modes, which for such a model would require a dimensionality less than 2. Here's another sign of unusual behavior, the E over T scaling in the magnetic fluctuations measured in these two different systems by Megan Aronson and Almut Schroeder, tells us that temperature is the only scale. This is what we would interpret as physics below the upper critical dimension, and yet the standard model has us above the upper critical dimension in 3 dimensions. Here is some more data showing how, as you go through this phase transition in serum rhodium indium-5, the Fermi surface jumps in its volume. And this jump in the Fermi surface volume measured by de Haaspen-Alphen tells us that the local moments are delocalizing. We don't understand why. And it's led to a lot of new ideas, the idea of local quantum criticality, a phenomenological idea of a two-fluid scenario, and one that I'm particularly passionate about, the idea that we need new forms of wave function to span between magnetism and itineracy, and this requires a new formalism. We've actually been playing with the idea of supersymmetry. Okay, I've got 5 minutes left. Let me talk a little bit about topological matter. But before I go on, needed a new theory of strange metals and quantum phase conditions. We don't even know whether they're phases or quantum critical points. And critical systems are an excellent starting point for the exploration of quantum matter. We talk about strange insulators, Kondo insulators. These are ancient insulators which have been affected by a new theoretical idea, which is the notion that band crossing can wind up the wave function and give it a topological twist. So that when you have an odd number of band crossings at the high symmetry point, you produce a topological texture inside the wave function. And it used to be thought that samarium hexaboride was a conventional insulator. It's been studied for more than almost 50 years. Here's some old data from 1965. Here is the resistivity measured by Ted Jabal's group at Murray Hill in those days, showing the growth of resistivity, the formation of a gap in sort of metal at low temperatures. And here is the persistent resistivity plateau that's been seen for more than 30 years, and no one knew that it was topological. We know this system has surface conductivity. The Hall constant derives from the surface. If you do non-local conductivity measurements, you can see that conductivity runs around the edges. And if you do ARPA's measurements, you can see some large Fermi surfaces on the surface, 3 Dirac cones consistent with 3 band crossings. Everything looks fine. However, there are a lot of anomalies we don't understand. Here's the phase diagram as a function of pressure. This system goes from a topological insulator into some kind of metallic state and then develops magnetic order at higher pressures. If you do neutron measurements, you see magnetic excitons. And the form factor of those excitons is particularly peculiar. It's a d-electron form factor, despite the fact these are formed from hybridization with f electrons. And we don't understand that. And even more mysterious, de Haaspen-Alphen shows 2 kinds of signal. Something that looks like a surface signal, which Liu Li and his collaborators have detected, and more recently, more accurate measurements have revealed the presence of also bulk oscillations, which may be due to magnetic breakdown, but maybe because there's something weird going on in the bulk. It's then a strange insulator. And one indication that something weird is going on is that the specific heat capacity has a large linear component that never goes away at low temperatures. It's been there for 30 years. You can grind the system up, and it shows the same linear specific heat capacity. And so there's a large density of low-lying states invisible to the neutrons. And this makes us wonder whether this could be a new kind of topological or strange insulator. Could it be that there are crazy types of insulating ground state which also have gapless excitations which mysteriously respond to a Lorentz force without giving a conductivity? That's an open question that we don't know how to answer at the moment. It's a matter of great controversy. So that really ends this. Oh, and there are many other systems which display resistivity plateaus in this category, okay? Maybe that's just junk. But most likely, these are also new kinds of topological insulators. And in these systems, we have reason to believe that the crystalline symmetry, the non-symmetric symmetries of the lattice, may be driving unusual conducting states on certain surfaces, but not all. So I'm going to end there, and that's my summary of the Kondo insulators. I'm not going to talk about uranium-lithium silicon to throw everything open for discussion. Thank you.
mention? Can you mention?
I can mention a few words about it. Okay, 2 minutes maybe. It's really been a fruit fly for new kinds of order, both really in the theoretical world. This has driven a tremendous number of new ideas. And we don't know whether some of them are right or whether we need something even newer. But here is the material. It has the same structure as the 122 iron-based superconductors. In fact, the ruthenium replaces the iron and the uranium are here. And if you measure the specific heat capacity, you see a whopping great big anomaly. There's a huge amount of entropy there, about 1/3 R log 2, excepting no one's been able to detect the order parameter. They used to think it was magnetism, then they found the moment was very, very tiny, and then they found the moment ceased to exist when they made the samples very pure, and well, a large amount of entropy, if you do the math, but no order parameter detected. Okay? So what's the nature of the hidden order? And there's been 25 years of theoretical proposals, many of which are based on the idea it might be a multipole, some kind of hidden multipole. But I'm one of the dissenters who believes it's not a multipole, but possibly a half-tupole, a fractional multipole. It's been a course célèbre for spectroscopies. We're going to hear about scanning tunneling microscopy. And one of the things that's really weird about it is that the G factor, instead of being isotropic like it is in most electronic systems, it's severely Ising-like. It actually has this G factor. Okay? You can measure it by various cunning ways. And so an Ising-like G factor in a tetrahedral environment is usually a signature of an integer spin. And the uraniums do have an integer spin, but how do the quasiparticles have an integer spin is the real question. And so the idea that we've been playing with is the idea that order parameters can fractionalize. And that this order parameter, just to finish off, is like an electronic Polaroid. Just as in a Polaroid you can polarize light, we think that the d electrons in this system, as they hybridize with the f electrons, are somehow acquiring integer spin character. And if they've got an integer spin character, that means the order parameter that links them has to be half integer. And so that's the idea that it might be a spinner. So even if this idea is wrong, okay, this has been a tremendous engine for new ideas, exotic forms of multipolar order. There's an entire Japanese consortium of research called J-physics, entirely based on exploring new forms of multipolar order, not just in cerium, but praseodymium and 5F systems. And we think that there may be many other examples of such hidden order. And so that in short, is the URS. Thank you for that question. I'll check it in the mail.
So Piers, you mentioned a few materials at the beginning which show superconductivity as well as possible quantum criticality. I was wondering if you could say something a little bit more about what you think the connection is between superconductivity, whether you think there's a connection at all, and if you do, why TC is so high in materials like cuprates and iron pentates.
Yeah, so I think there's a furious debate in the field, and one idea is that when you're at a quantum critical point, you get soft fluctuations. Those provide the glue, and that drives the pairing. I think it's a very prominent idea. Another idea, which would be the other extreme, would be that you release the spin degrees of freedom, which have been bound up inside the antiferromagnet, and you provide they're now available to entangle as you would like. And that entanglement now drives, amongst other things, superconductivity. And in between those two extreme limits is a spectrum of different opinions. Could be exotic types of fluctuation, could be new kinds of quantum critical point. But we do see examples of quantum critical point where we don't see superconductivity. And so there is that question, well, why doesn't it work in all cases? So I didn't answer the question, but I did give an overview of what the debate is. Yes, Catherine.
Yes, because I'd like if you could say a bit more about the controversy about samarium hexaborite. For the quantum oscillations.
Yeah, so I'll just.
Thermodynamics. What's your view on that?
So my view is evolving. I'm very annoyed with the experimentalists for not sharing samples. And I really wish they would do this more, because we have a situation where the most exciting data hasn't been reproduced by another group. Okay? But I do believe it's good, that data. I do believe that data is good. I believe that there are different sample types which show different oscillation structures. So it may well be that you have the conservative, boring, fully gapped, uninteresting topological Kondo insulator, or it may be that there is the possibility that you really do have a bulk state which has gapless excitations, some kind of quasi-Fermi surface. This is the wild possibility. And I do think it's worth an investment of time to explore that possibility a little bit further. So my view on this has changed a little bit. A year ago, Bhaskaran pointed out to me that we had written a paper on samarium hexaboride years ago, which we never published, on Majorana fermions. He said he got it right, and I disagreed with him. But more recently, we've actually gone back to that model, which we thought was a superconductor, not an insulator, and we've been having second thoughts, and that's partly my question that I raised in the previous talk. If you kill a superconductor, could it become an insulator? Could it be that samarium hexaboride actually is a failed superconductor? We're working on that idea at the moment. We can show that we can make it topological, but we can't prove yet that it's not a superconductor. But one of the ideas here is that the when you have exotic forms of superconducting order, they may have different topologies. So superconductivity is sustained by the fact that the order parameter is a U1 order parameter, has stable vortices. But if the order parameter ceased to be a U1 degree of freedom, if it became a spin or a spinner, then it would no longer have stable vortices, and so you'd wind up the phase and it would decay on some time scale. The current would disappear, vanish. If it disappeared very, very slowly, you'd say, oh, I've got a metal. If it disappeared very rapidly, you'd say, oh, I've got an insulator. And so that's an idea that we're pursuing at the moment. Students? No, Jed, almost a student.
So you flashed the E over T scaling for two different compounds?
Yes.
And one I think is strongly disordered?
Yes.
And one is not. So would you say that there's two different paradigms for these type of quantum critical points, whether they're... What's your opinion on that, I guess?
You know, Daniel Fisher would, in days when he used to work on quantum matter, would always say, look, disorder's always strongly relevant, and you just can't escape from it, so that every system is disordered. That might be true, but of course, in the meantime, experimentalists have worked so hard to increase the resistance ratio, and they've shown that as they reduce the residual resistivity, the strange behavior continues. And so I think you and I share a common view, which is that there may be something very local in the strange metallic behavior, which is robust against disorder and occurs in both disordered systems and in very pure systems. And so I think most likely they're the same phenomena in those two examples. Of course, it's much easier to do neutrons on powder than it is to do neutrons on crystals. The second example was a single crystal. The only example, to my knowledge, where E over T scaling has actually been seen in a single crystal. Yeah.
So this is also a question about dimensionality. So you emphasize that one sees E over T scaling
yes.
in materials which naively ought to be above their upper critical dimension. In the spin density wave kind of approaches to this, I mean, people have looked at putting the Hertzsprung boson propagator into the fermion self-energy, trying to figure out how you get the non-Fermi liquid. Mm-hmm. There was this work by Reck et al., some of whose collaborators are in the audience, which suggested that omega to the 2/3 might be exact, but then there was this stuff by Sung-Sik Lee and Metlitsky and Sachdev that showed that that large N didn't work out because you had these hidden kind of dangerous forward scattering processes in the diagrammatics. If I sort of blur my eyes a bit, forward scattering sounds a bit like reduced dimensionality. Do you think there's any connection between that story from the spin density kind of approach and seeing lower dimensionalities than we expect in the experiment?
This is a great question, and it opens up a vast panorama of possibilities, as you know. And of course, you can't escape from the fact that you've got translation invariance, and you do live in a not zero-dimensional, but a three-dimensional world. Okay, so you've got to explain it in that context, and that's, in that sense, even if you did produce a local quantum critical picture, it wouldn't solve the problem. For me, I always go back to what I consider to be the biggest unsolved problem and the most neglected problem of our era, which is the normal state of the cuprates at optimal doping. Okay? No one talks about that. If you go to a modern workshop or conference on the cuprates, everything is focused on the pseudo gap, because everybody knows if you solve the pseudo gap, you solve the whole problem, except we've been trying to solve it for 20 years now, and we haven't solved the whole problem. And the problem with the normal state of cuprates is there are two relaxation times, a linear one, which we don't understand, and a quadratic one, which governs the Hall response. And you see that also in the 115 materials. You see it in interface materials. And Jim refuses to measure the Hall constant of the iron-based superconductors at the quantum critical point, but maybe you'd see it there if you did do the measurement. And so I think it's a burning issue, and it does involve, just to get you wound up, it does involve bringing in the Fermi surface. The Fermi surface is there, but it's weird. And so, yeah, you've got to think of new ways of doing the quantum criticality around the Fermi surface and think about exotic transport phenomena. And so maybe symmetric borate connects up with that, because it's an example of a system with two relaxation times, one of which is so fast it thinks it's an insulator. Yeah, Jim, you were going to comment.
Oh, well, I'm glad you appreciate how easy those experiments are. But I think one thing that we are working on is exactly that problem, and it turns out that the properties of the iron pnictides and the Hall effect are actually almost identical to what's seen in the cuprates at optimal doping as well, in terms of the way the Hall coefficient.
Will you show us that data at this meeting?
I can show it to you after this.
Okay, I'd love to see it. I think everyone would love to see it.
Well, I'm not talking about that.
So this is something that seems strange to me. When you talk about the quantum criticality and the two models of the spin fluctuations and the delocalization of the spins, you always talk, and Chris also is talking as though the Fermi surface is a stable object. But we know, at least in the heavy fermions, that at the quantum critical point, the Fermi surface itself is unstable. It's balanced between two different volumes of Fermi surface. But I don't know of any theoretical work on this. Maybe Cento published one paper several years ago.
So that's absolutely right. There's a phenomenological paper by Cento to talk about critical Fermi surfaces. And there's nothing beyond that at the moment. I mean, maybe I'm being unfair, maybe it's something I'm not aware of. It's one of the reasons is that when theorists try to deal with critical behavior, they need to know what they're fluctuating against, right? That means you need to have a good description of the wave function or the ground state on both sides of the problem. And we don't have a wave function that spans the two sides. And so that's part of the problem. Peter?
So on this proposal that the order parameter is a spinor, so what experiment would one have to do to verify or falsify that?
Well, I mean, unfortunately, one of the predictions we made has falsified the theory, which was that there should be a very tiny transverse moment, which is just not seen in experiment. But presumably, there ought to be the possibility of quantum interference experiments that can tell whether an electron is neither half integer or integer in character. As you know, the half integer character of an electron leads to localization, for example, and if you start to mess with it by putting in spin-orbit coupling, you can have anti-localization. So maybe something in between could occur in the system if you can understand the localization properties. And maybe there would, that's a very vague answer to your question. I don't have a good answer.
Okay, well, we're right on time, so let's thank Piers again for a very wonderful